other screen. Okay. All right. No, we have too much left to do. We have way too much left to do. And yes, you guys do have a test that's hanging out there. I knew there was something else I needed to mention. There's a test out there. And you do have a test. But all right. So where we were on Friday is we had talked about, and I'm actually going to use different colored markers. We had talked about that if I have like charges, so if I have a positive charge and a positive charge, they're going to repel. If I have a negative charge and I got it recording, so we're good, and a negative charge, they're going to repel. But if I have a positive charge and a negative charge, they're going to attract. And we talked about parallelism, where the force is equal to Newton's law of, or Newton's universal law of gravitation, mass 1, mass 2 over r squared. Now, what I am not 100% sure that you guys did in General Physics 1, if I have an object here, and this object, we're going to go ahead and call this 6 kilograms, and it's located at a point, we're going to do this as 0, 4. And then I have an object that's 2 kilograms, and it's located at 0, 0. And then I have an object over here, and we're going to call that 10 kilograms. And this one is located at, we're going to make it 5, 0. And we wanted to know the force on this particular object. Did you guys do any of these last semester?
No, I did.
I know you did, but I've got a lot of blank stares. Okay, so if I did those forces, I'd have to calculate the magnitude of the force. So I'm looking at the force on this item. And these two things are attracted because we're dealing with masses. And these two things are attracted because we're dealing with masses. So the resultant force is going to be something that looks like that. But I'd have to calculate the magnitude of that force, and I'd have to calculate the magnitude of that force, and we're having to add our vectors, and we've got all of those lovely little pieces associated with it. So the question, that's what we've got. Now, for our charges, which we talked about and went through this, I've got my charge is going to be K, where this is Coulomb's constant. And I've got charge 1, charge 2 over r squared. And this is going to be in the r direction for my two charges. Now, K, this Coulomb's constant is 8.99 times 10 to the 9th Newton meters squared, Coulombs squared. My G for Newton's gravitation constant . 6.67 with lots of other ones times 10 to the minus 11 Newton meters squared kilograms squared. So if we're looking at these things, I want you to notice the coefficients here. 10 to the minus 11, 10 to the 9th. So we could actually do this for a hydrogen atom. And my hydrogen atom has a proton and an electron, and the radius is the Bohr radius. And if we did that, lovely. And my Bohr radius is typically on the order of 10 to the minus 15. And you guys do have this example in the book. And I think I have I've done this problem multiple times. So there are videos out there for this. But if I use this as the Bohr radius and I get my force due to electrostatics, it's on the order of 10 to the minus 8. And my force due to gravity is on the order of 10 to the minus 47 in the R direction for my atoms. So I don't really have to worry about my mass attraction in my atoms, because this is so much different between those two items that I can disregard my gravitational force when I'm doing that, if I'm dealing with atoms and things like that. Now, what's interesting is I can't disregard that. I can't disregard that if I am doing van der Waals forces, because van der Waals forces are also going to come in here, and they're going to be more on the order of electrostatic. So as we start dealing with chemistry stuff, we are playing with those electrostatic things versus gravitation. But if I'm dealing with planets, stars, massive objects, gravitation, then it's going to be out there. But this is where electrostatics gets fun. So we're going to start with a positive charge. And this is going to be 5 microcoulombs. I'm going to have a negative charge. And my negative charge is a negative 3 microcoulombs. And I'm going to have another positive charge at, we'll make that 4 microcoulombs. We're going to give ourselves a distance here. I'm going to make this 0.5 meters. I'm going to make this 0.25 meters. We're going to look at what is the force on this charge. So the first thing we're going to have to do is we're going to have to look at our situation. This is a negative charge and it's being attracted this direction. It's a negative charge, but it's also being attracted in that direction. So my resultant force, there's my red one, there's my green one. I'm going to have some sort of a resultant force, but I don't know which one's going to win out, because it's like playing tug of war. So if I were dealing with my forces along a tug of war string, the question is, which one is that going to be? So how you approach these problems are like this. We're going to calculate the magnitude of the force. It's going to be my K Q1, Q2 over R squared. This is going to be my 8.99 times 10 to the minus 9. Is that right? No, 10 to the plus 9. Newton meters squared, Coulomb squared. Now, for a lot of this stuff, folks, you may want to use 9. WebAssign has been particularly persnickety. I think it's getting very persnickety in the sense that if you're dealing with significant figures, for example, I've had several people have a problem where they've had 0.67 and they've typed in 0.07 and it's been counted wrong. Well, that's because it's doing it off of a plus or minus 10%. And that's greater than a 10% error if you're dealing with significant figures. Not sure what the change that WebAssign has made of recent dates, but historically, I never had trouble using my 9 times 10 to the 9th to do my calculation here. But that might be something you guys are going to run into given what WebAssign's been doing lately. So now we're going to put in this one, we're going to do this between our 5 and our -3. So I like to either use my charges to represent what my force is when I'm doing it in my subscripts. It just helps me keep track. And we're going to do our 5 times 10 to the -6. We don't have to worry about this because we're dealing with a magnitude. So I'm just going to do my 3 times 10 to the -6. And we're at 0.5 squared. And there's my meter squared. There's coulombs times coulombs. So that's all working out nicely. And if you don't remember working with exponents, okay, so I have 10 to the plus 9. I have 10 to the -6. I have 10 to the -6. That's going to give me 10 to the 9 minus 6 minus 6, which is going to give me 10 to the -3. And so now I just have to type into my calculator 8.99 times 5 times 3 divided by 0.5 squared times 10 to the -3. This gives me 539.4 times 10 to the -3. Gives me 0.54 newtons. Now you see why we use microcoulombs. It just makes life a little easier. But this comes in handy, remembering how to deal with your exponents. That comes in very handy depending on your calculator. And when I'm working with my general physics 2 students, who have trouble manipulating their calculators, you want to kind of keep track of those things, because if they're not using their calculators correctly, they may get order of magnitude issues associated with what they're doing because of how your calculator's entering in the number. So now we're going to get our -3 and our 4 one. So that's going to be my 8.99 times 10 to the 9th Newton meters squared coulombs squared. I've got my 3 times 10 to the -6. I've got my 4 times 10 to the -6. I have that divided by 0.25 squared. We're going to end up in newtons over here. And I get 1.726 newtons. So my resultant force is going to be the sum of my forces. And now I go in and I put in my direction. So this one is going to go to this direction. This one is going to that direction. So now I'm going to have my 1.73 newtons minus my 0.54 newtons. It's going to give me 1.19 newtons, and it's going to be going in that direction. Everybody got it? Now we're going to have more fun. I'm going to put a positive charge up here. I'm going to put a negative charge over here. I'm going to put a negative charge over here. This is going to be 1 meter. And this distance right here is going to be 0.5 meters. We're going to have this one be a negative 8 microcoulombs. We'll have this one be a negative 6 microcoulombs. And we're going to have this one be 10 microcoulombs. So we know from our picture that this one is going to be attracted that direction. This one is attracted that direction, and we want to find the resultant force on this charge. We're going to find the resultant force on that charge. Well, first thing I got to do is I got to figure out what my R is. So we remember that A squared plus B squared is equal to C squared. So C is going to be the square root of 1 squared plus 0.5 squared. From what I get is 1.12, and that's in meters. So now I can calculate my force, the magnitude of my force from my 6 to my 10, because that side is the same as that side. The way I've got that one, the way I've got this one drawn, I can use symmetry.
Then A squared B half.
Well,
Put it as 1.
well, oh yeah, you're right. You're right. So let me do that again. So it's 2 times 0.5 squared. That's going to be 707. So I get 8.99 times 10 to the 9th Newton meters squared, Coulomb squared. And now I've got 6 times 10 to the minus 6. I have 10 times 10 to the minus 6. And then it's going to be my 0.707 squared. This gives me 1.08 newtons. Gonna do the same thing for my 8 and my 10. This one gives me 1.44 newtons. All right, but those are the magnitudes. So if I want my vector, that's my 10. This is going to be my 1.08 in the I direction, but I have to put in a factor here. And that's actually going to go negative because I'm going in the negative X direction. I'm also going negative down. I'm going to get my 1.08 and I have to put in my factor here. And I get my J. Here's where life becomes fun. Cosine of the angle is equal to the adjacent over the hypotenuse. Sine of the angle is equal to the opposite over the hypotenuse. If I am looking at this triangle, and that's the angle that I want to get my X component, there's the opposite, so that's 0.5. My hypotenuse is 0.707. I don't have to take the step to go back and figure out what my angle is. You can go back and figure out the angle if you want. I don't have to do that. I can use this relationship to get me my ratios for my vectors. So for this one, and I just happen to pick a nice one, it doesn't really matter. I'm not going to get myself discombobulated and backwards. But at least in this case, I can actually go back and say, all right, I got it. Because I got a nice isosceles triangle. But this is helpful. And you're going to find this shortcut very helpful as we move into statics next spring. And we don't usually show people that for a while, but you might as well learn it early on. So I got 1.08 times 0.5 divided by 0.707. And that one's going to give me a negative 0.764 in the I direction. And that's going to be the same because we got a nice isosceles triangle. Life is good. So that gives me that one. So now I can do the other one. And I got a nice isosceles triangle in the same place. So that works out really well. So this one is going to give me, and this time I got a positive in the X direction. And that's my 1.44 times my 0.5 divided by my 0.707 in the I direction. And then I've got a negative in the Y direction. And I get 1.02 in the I direction minus 1.02 in the J direction. So now I'm going to do my adding of my vectors. (1.02 minus 0.764. This gives me a positive 0.256 in the I direction. And I get a negative 1.784 in the J direction. And then we can use our normal ways to do our calculating the overall magnitude and direction. But if we look at this, we're going to have slightly, our resultant vector is going to be more to this direction than it would be to that one. You guys don't do fields in the same chapter. So we will stop there. This page.